Hello everyone. As we accelerate toward a clean energy future powered by green hydrogen, the reliability and performance of electrolyzers stand at the heart of this transition. Today, I want to shine a light on some of the critical, often overlooked aspects of electrolyzer projects: operation, stack degradation, gas crossover, and water purity. These are not just technical concerns, they are the very factors that determine efficiency, uptime, and ultimately the success of hydrogen as a scalable energy solution. Let's explore how careful design, precise control, and a focus on quality can help us unlock the full potential of this remarkable technology. Electrolyzers are usually connected with the grid, and the grid connection cost is influenced by various factors. One of the primary considerations is the voltage level of connection. For instance, connecting at 11 kV may be suitable for shorter distances and lower loads, while 33 kV is often preferred for higher power requirements or longer transmission distances that offers better efficiency and lower losses. The distance from the grid substation directly impacts the cost, as longer runs of medium voltage cables and associated infrastructure significantly increase installation and civil engineering expenses. A thorough feasibility study and early engagement with the local distribution network operator or transmission network operator are crucial to factor in the correct costs for your project. Green hydrogen electrolyzer unit requires direct current, which means the three-phase, alternative current, is then converted by a rectifier into direct current, DC. The electrolyzer stack efficiency is usually calculated by dividing the amount of hydrogen produced and electricity used. The production efficiency is directly proportional to the power in kilowatt-hour. The thermodynamic efficiency would drop if the cell supply voltage were changed due to any reasons. The stack efficiency is directly proportional to the current density. The trend with the passage of time shows the change of cell voltage with current density, which would affect the cell stack efficiency and the overall production efficiency. 50 to 55 kilowatt-hours per kilogram of hydrogen or 4.5 kilowatt-hour NM3 referred in the literature is usually based on theoretical calculations and is the ideal number, but practically this number is different as there are so many variables that influence the production efficiency in the real world, like balance of plant, utility power, stack catalyst degradation, plant downtime, thermal protection, etc. The actual production efficiency could be anywhere between 60 to 70 kilowatt-hour kilogram or 5.40 to 6.30 kilowatt-hour NM3 depending on the age of the plant. The best way to confirm this is by closely supervising the factory acceptance test or checking the historical operational data of an electrolyzer. Over time, proton exchange membrane electrolyzer stacks experience gradual performance degradation, primarily due to the physical and chemical wear of key components within the cell stack. This phenomenon, known as stack degradation, results in a slow decline in efficiency, typically observed as an increase in the voltage required to produce the same amount of hydrogen. Factors such as high current densities, prolonged operation at elevated temperatures, and inconsistent humidification of the membrane can accelerate this decline. Additionally, the degradation of precious metal catalysts, membrane thinning, and gas crossover contribute to reduced hydrogen output and increased energy consumption. Gas crossover in PEM electrolyzers is a critical degradation phenomenon where hydrogen and oxygen gases permeate across the proton exchange membrane, leading to reduced efficiency, compromised gas purity, and in severe cases, safety risks or catastrophic stack failure. This issue typically arises when the membrane loses its selective permeability due to mechanical thinning, pinhole formation, chemical degradation, or poor humidification. High operating temperatures, excessive pressure differentials between anode and cathode, or prolonged exposure to dynamic load conditions can accelerate membrane fatigue and increase gas permeability. Moreover, inadequate water quality, presence of reactive contaminants, or aggressive start-stop cycling can chemically damage the membrane structure, further increasing the likelihood of crossover. When hydrogen and oxygen mix within the cell, not only does it reduce hydrogen yield, but it also creates a combustible environment that may trigger alarms, force shutdowns, or damage stack components. Preventing gas crossover requires maintaining optimal membrane hydration, controlling pressure balance across electrodes, using high-purity deionized water, and avoiding aggressive operating regimes. Routine diagnostics, such as gas purity checks and electrochemical impedance monitoring, can help detect early signs of crossover and mitigate major system downtimes through timely maintenance or membrane replacement. Impurities in feed water, frequent start-stop cycles, and exposure to contaminants can further impact the stack's health. Understanding and managing these degradation mechanisms is critical for optimizing electrolyzer lifespan, minimizing operational costs, and ensuring reliable hydrogen production in dynamic grid or industrial applications. PEM electrolyzers require ultrapure water to function efficiently and protect the integrity of the membrane and catalyst layers within the stack. The typical standard is better deionized water, with conductivity less than 0.1 microsiemens per centimeter. This high purity is essential because even trace amounts of impurities can be detrimental that can catalyze membrane degradation, foul catalyst surfaces, and permanently damage the ion-conducting pathways. Organic contaminants and microbial growth may also clog the system or produce gases that interfere with electrolysis. These impurities act as poisons that accelerate stack degradation, reduce hydrogen purity, increase energy consumption, and shorten operational life. Sometimes drastically if not detected early. Continuous water quality monitoring and scheduled maintenance are crucial. By ensuring consistently high water quality, the lifetime of PEM stacks can be extended significantly. In summary, the long-term performance and reliability of PEM electrolyzers depend heavily on careful management of operating conditions, particularly stack health, gas crossover prevention, and water purity. Through robust system design, precise control strategies, and robust water treatment and monitoring protocols, operators can extend stack life, ensure stable hydrogen production, and maximize the overall efficiency and return on investment of proton exchange membrane electrolyzer systems. Thank you for watching my video. Please do consider sharing this video with your friends and give it a thumbs up. To see future video contents like this, make sure to hit the subscribe button. Also, if you want me to cover any specific topic in the future or have any further questions related to the topic, please leave your note down below.